Every single day, thousands of tons of liquefied energy carve through heavy ocean swells, making their long journey toward Indonesian ports. The country's domestic economy runs almost entirely on liquefied petroleum gas, or LPG. It fires the stoves of millions of households and small businesses, creating a deep structural reliance on an imported commodity. These weathered green 3-kilogram cylinders are an inescapable daily requirement. They represent the baseline energy foundation for the population. Sustaining that foundation requires a staggering volume of fuel. In 2024 alone, Indonesia had to import approximately 8 million tons of LPG to meet consumer demand. That physical volume translates directly into a severe macroeconomic toll, draining 63.5 trillion rupiah from the national budget in a single year. This localized energy deficit creates a massive bottleneck for the broader national trade balance. Buying millions of tons of foreign gas continuously bleeds the state's foreign exchange reserves. Relying on an international supply chain for a non-negotiable domestic necessity creates an unsustainable financial model that requires a systemic engineering intervention. The paradox of this financial drain is what lies directly beneath the ground. Indonesia possesses a massive 38.8 billion tons of domestic coal reserves. Extraction operations across South Sumatra and Kalimantan require massive industrial footprints, moving millions of cubic meters of earth to reach the coal seams below. But there is a critical geological caveat. 65% of this reserve, over 25 billion tons, is low-rank coal, encompassing lignite and subbituminous variants. Low-rank coal is geologically young and physically inferior. It is highly porous, holding an extreme water content between 30 and 70% total moisture. Because of this trapped water and loose structure, its energy output is heavily compromised. It yields a severely lower calorific value, falling under 5,700 kilocalories per kilogram, far below premium export standards. It also carries a dangerous logistical flaw known as swabakar. Its reactive nature makes it prone to spontaneous combustion, rendering it hazardous to store or transport over long distances. These compounded physical defects mean the international market has little interest in buying it. 25 billion tons of this low-grade rock remain geologically trapped within the country's borders, a massive, stranded asset. The solution is to abandon the idea of burning this low-grade rock for raw heat. Instead, engineers can chemically deconstruct it and upcycle it. This is achieved through a thermochemical process known as gasification, forcing a phase change that strips the solid mineral down into a synthetic gas. Inside a gasifier reactor, solid low-rank coal is continuously injected alongside high-pressure steam and pure oxygen. The internal chamber is subjected to extreme heat and pressure. These thermodynamic conditions physically break the molecular bonds of the coal. What emerges from the reactor is syngas, or synthesis gas, a raw, volatile mixture consisting entirely of carbon monoxide and hydrogen. Gasification standardizes the feedstock. It removes the moisture and structural flaws of low-rank coal, leaving behind consistent, high-potential chemical building blocks. Those raw chemical blocks must now be assembled into a stable, complex molecule, Dimethyl Ether, or DME, carrying the chemical formula CH3OCH3. This diagram illustrates the two primary methods for this synthesis. The legacy method is the indirect process, which forces the syngas through two separate sequential chemical transformations. First, the syngas flows into a reactor coated with a copper-based catalyst, which forces the carbon monoxide and hydrogen to bond into liquid methanol. Second, that methanol is moved into an acid catalyst chamber, often utilizing zeolite. Here, it undergoes dehydration, a strict water removal process that strips an H2O molecule away, yielding the final DME product. Modern, massive-scale industrial plants often opt for the direct process instead, routing the syngas into a single, highly advanced reactor. This reactor uses a bifunctional catalyst that simultaneously performs both methanol synthesis and dehydration in one continuous thermodynamic loop. Regardless of the pathway, the resulting dimethyl ether possesses highly specific physical traits. It remains a gas at room temperature, but liquefies easily when placed under medium pressure. By mastering these catalytic pathways, engineers have successfully synthesized a chemical analog to petroleum gas out of seemingly worthless coal. The hardest part of adopting a new national fuel isn't the chemistry, it is the immense cost of retrofitting existing consumer infrastructure to burn it. Because its characteristics closely mimic LPG, producers can blend DME into existing gas cylinders up to 20%, requiring absolutely no modifications to standard stoves. Transitioning to 100% pure DME only demands minor modifications to rubber seals and burner rings. Beyond household use, dimethyl ether possesses a secondary capability replacing heavy industrial diesel engines. It inherently lacks sulfur and boasts a cetane number between 55 and 60, exceeding conventional diesel. This results in a cleaner combustion process that drops particulate matter emissions to practically zero. DME is highly versatile. Its drop-in flexibility allows integration with existing infrastructure, providing a single chemical solution for both household cooking and industrial transport. To move from theory to physical reality, the government mapped 6 zones for downstreaming, anchored by the massive Tanjung Enem pilot project in South Sumatra. State enterprises PT Bukit Asam and Pertamina have heavily committed to this specific site, earmarking 800 million tons of low-rank coal exclusively to feed this facility throughout its lifespan. This facility is engineered to ingest 5 to 6 million tons of low-grade coal annually. Through gasification, that raw input is compressed into 1.4 million tons of dimethyl ether. Starting around 2026, this output will permanently cross out 1 million tons of imported LPG. The Tanjung Enem project demonstrates that thermochemical upcycling is a viable strategy for macroeconomic defense. It proves that with precise engineering, a stranded geological liability can be processed into sovereign energy independence.